Welcome to another episode of Peep and Eep, an EIP dedicated series where we discuss an Ethereum improvement proposal and understand why that is important for Ethereum blockchain. I'm super excited to welcome today's guests, Sam Wilson and Ansgar Dietrich, who are authors for EIP 2938. Along with them, we are joined by Light Client, Alita, and William. So, for those who are new to the show or this proposal, we already have recorded an episode, episode 12 on account abstraction, with a wonderful presentation by the authors that you are going to see in this meeting as well. You can find the link of the episode on the card on your screen and also in the description box. There are some good question answers that might be of your interest. So if you haven't watched it already, it is highly recommended to watch episode 12 of Peep and Eat before this one. Welcome once again, Sam and Ansgar. I think having a quick intro followed by summary of a proposal would be good to kick off the meeting today.
Sounds good. Hello, everyone. I'm Ansgar, and Sam and I basically are here today to present basically the second part of our EIP walkthrough. Maybe quick intro again. We are part of the Quill team at ConsenSys, doing like mainly Ethereum protocol research there, and the kind of abstraction was one of the main things we did in 2020. So here we are. And then for like I think I'll mostly skip through the first part, of course, that we already covered. Basically, I mean, at this point, if you reach this point, you should know at least on a high level what a card abstraction is. So the idea again, it's just basically abstract away the validity conditions, make them programmable, basically allow for contracts to send transactions, if you will, right? And we had all these nice little pictures, and then. So basically what we, I think the last thing we covered in detail on the last call, that is the actual implementation as far as the protocol is concerned. So basically the thing to maybe reiterate here and to kick things off with is this kind of this divide again, where our design approach with a kind of abstraction was to basically keep the protocol changes minimal. And protocol changes, again, basically meaning those consensus rules that govern how exactly transactions have to be executed, right? What is a valid block and what isn't, basically. So basically this very critical part of the blockchain that basically where every single change really requires a lot of attention, we wanted to keep that the one very small. And I think we went through the EIP as well for quite here's the EIP, by the way. We'll switch to that soon, but just basically to kick off, I have the presentation on the side as well. But basically we went through the specification quite a bit. So the main thing really is this pay gas opcode that signals if a contract has a kind of abstraction transaction start at the contract, then it can call pay gas to signal I'm willing to pay for the transaction. And a contract has to do that, otherwise a kind of abstraction transaction is invalid, basically. If the contract decides it doesn't want to pay, then it's invalid. But basically, there are a few details, of course, but with that, basically, you get from the protocol side, you already get card abstraction basically done. That's it, basically. It's really just the new transaction type, contracts, consent, transaction. That's the story as far as the protocol is concerned. And then, and I think on the last call, we very briefly went through this piece, but basically just like because we were running out of time just a little bit, so this is probably the best point to kick it to take it back up is why is the story not just over here, right? If it was so simple, I think we would have had a kind of abstraction for quite a while now already on Ethereum, but it's not quite as simple, and so maybe to understand that it makes sense to very briefly think about like what would happen if individual nodes in the network were just basically not bothering with account abstraction transactions, right? So usually what nodes do in the Ethereum network, if a new pending transaction is sent to them, they'll look at it, and if it looks good, they just broadcast it to other peers, and they keep it around and so on until it either at some point makes it into block or it gets dropped because it's too basically too low paying or something. But basically, if nodes were to not do that at all, and this is, by the way, this is called the mempool, right? I think some people on last call weren't quite fully familiar with the word. So mempool basically is just the part of the client software that deals with pending transactions. So what if basically nodes would not bother with account abstraction pending transactions whatsoever? At that, if that was the case, then account abstraction would be perfectly safe, right? Because the only way nodes would have to be bothered with it basically is if a new block comes in and for some reason the miner had decided to put in a account abstraction transaction in it, right? No matter how they got the transaction, but let's say that the miner just either created it themselves or on some side channel got an account abstraction transaction, included it, and it would be no issue whatsoever for node to execute it, right? It's the exact same kind of rules that already govern other kind of transactions. You just, if it never calls paygas, it's an invalid block. If it reaches paygas, then it's basically it's valid as far as that is concerned. Then you execute the transaction as normal, you apply all the effects. So it's basically like totally normal thing. So from a node perspective, validating a block with an A transaction in it just feels very normal. So there's nothing much that changes. The thing that's tricky about account abstraction is now to kind of basically allow this kind of the mempool support for account abstraction transactions. So of course, otherwise the whole thing is kind of pointless, right? If the network doesn't forward account abstraction transactions, it's nice that we have the support in the protocol, but like you need a way for your transaction that you create to actually reach miners and everything. So we really need this mempool support. And why is this tricky? This is what this nice little table was here for, and I think we walked through it last time briefly. So the idea is basically there are three different ways in which processing pending transactions or new incoming transactions that you haven't seen before can be tricky. The first one is just malformed transactions. So let's say it doesn't even it's not even like, it doesn't even look like a valid transaction. You just immediately drop it. That for normal transactions, for legacy transactions, and for AA transactions, that both is very like inexpensive. That's not an issue. But then it gets a little bit more tricky with invalid transactions. So say the transaction looks, it's well formatted and everything, but it turns out the signature is invalid for non-AA transactions. You can check that in very short time, right? So basically an ECDSA signature check that is very quick. For account abstraction, it's a little bit more tricky because you actually have to basically run the transaction until the contract either just decides it doesn't want to pay and just stops execution, but it could basically, there's this kind of validation gas limit. So basically a contract could take, I don't know, let's say 100,000 gas before it decides, or before it doesn't decide to pay for the transaction, right? It either just runs out of gas or it stops, but it consumed a lot of gas. And then of course, running the transaction for quite a while before it reaches that point is a little bit more expensive. I think I shared with you last time, we had this DOS study as well. There's kind of we had a study where we looked at like real world impact. We implemented a prototype of account abstraction. We did exactly this. We basically just bombarded nodes with a lot of invalid transactions, just looked how much resources were consumed. And we did determine that it's a little bit higher of an effort for nodes than normal transactions, but it's still basically all within limits. So this is not the critical part either. But you're already seeing this will be where the problem lies. So what's the third issue? And this is a little bit tricky because the third one is something that just doesn't really happen with normal transactions, with the legacy transaction. It is valid transactions. So like you see a transaction, you process it, it looks like, yep, you could right now, this could be included on chain. And then you again, what nodes do is they put it in their mempool, like they keep it locally, and they also rebroadcast it to all the nodes they know, and then they broadcast it, and it basically makes its way through the network.
So I'm just going to jump in here for a second, Ansgar.
Good, yes.
I was going to ask a question.
Yeah, go for it. Yeah.
I think it'd be helpful to understand why it's a problem that a node, like why can't a node just have infinity transactions? Like why is there a limit to a mempool, or where does that problem come from?
Yeah, that's a good question. I would say that's two parts. So for one, I think it's always important to keep in mind miners as one very important subset of the nodes in the network. And miners basically want to only keep valid transactions locally, because at the time that they want to create a new block, they want to go to the mempool, say, give me the highest paying transactions, and then they want to just execute it and start mining on the block. If in their mempool, all of a sudden, basically 90% of transactions are not valid anymore, then they would basically have to go through them, execute it, see, oh no, it's not valid anymore, discard it, go through the next one. So it would take a lot of time before they can actually have a valid block they can start mining on top of. So it is really important that you have like a good way of keeping your mempool sanitized with only valid transactions. And then in general, why don't you want an infinite amount of valid transactions even? That's really just like a resource thing. So you just basically want to not you don't have infinite memory, you don't have infinite disk space. So this is why, no, it's usually right now, I think Geth keeps around, like, is it 6,000? I think it's like, yeah, something of that's on that order. With default settings, you can of course change that, but it's something like 6,000 valid transactions at any time.
I mean, haven't we discovered that there are generalized front-running bots that are scraping the mempool at any given moment? They seem to be able to process all of those transactions pretty fast. Miners don't have the same kind of resources.
Oh, they do, but so basically for front-running bot, so let's see. So basically for miner, every like little fraction of a second that they spend extra before they can start mining, that is just like a revenue loss, because that just decreases your probability of discovering the next block. Whereas for front-running bots, that's really just like everyone has to basically contend with the same problems. There's no way to basically figure out if a transaction is front-runnable or not before you actually looked at it. So this is just like a price everyone has to pay to do.
I wasn't talking about stopping the front-running bots. I was just saying that if a front-running bot itself is able to process all of the transactions in the mempool to discover transactions which should be replayed in front-run, that means that they do have the capacity and the resources to keep up with high volume and to process transactions very fast in order to find profitable transactions, let alone just finding transactions that are valid as opposed to invalid. Is it really a resource issue for miners to be able to sift through and find what's valid and what's not?
So that's not exactly true. So if a front-running bot falls behind for a little while, that's perfectly fine. They just catch up and start front-running, more later on. But for a miner, they would lose. Well, I mean, a front-runner would also lose out on revenue, but like it's the same kind of problem. If you can't keep up consistently as a miner, you lose a lot more value, I think.
Also, I think there's might be a slight kind of difference here that's easy to overlook. A front runner like processes every transaction once. So like a new transaction comes in, they didn't see it yet, they look at it once and check, is it front runnable? And if yes, they do some special thing with it. But for 99% of transactions, the answer is no, and they just never look at it again. That is what every node already does. So this is fine, processing every transaction once. What you just want to avoid is having to process a transaction multiple times. So once when you basically receive it, and then later on again when you want to create a block or something, because then it can be a problem, and then it can also be a concentrated problem, because it could be that you are targeted, and in a way where if you didn't sanitize your mempool and you kept around transactions that are now invalid, it could be that there was some kind of attack where you basically now all of your mempool is invalid, right? Because you were sent a lot of transactions that then later on were all invalidated or something. So you could just basically be unable to mine at all. You could be targeted, and people could just basically shut down your mining operation.
Or your node has too many. Maybe could I offer an analogy that I think might be helpful?
Sure.
Like if every node is getting envelopes of transactions, like imagine that they're getting an envelope, and the first thing they do is they have to open the envelope and read, like, is this transaction good, or is it like, will this work or will it not work? And if they can quickly sort these envelopes into, I can ignore you, I can hold on to you, and then they stay green light or red light, then that's kind of what the network does today. And if a node can only handle so many envelopes at once, and if it has to go back to recheck an envelope, if there's like this gray area, then it adds like more going out, like the second pass of checking the envelopes or checking the transactions is where like we don't know what's going to happen. So when like usually when we get to this point in the core devs discussion, it's this, if you're doing one pass for everything and this kind of deterministic at the end, everybody knows that all these transactions are going to be green and all these ones are red, so we can ignore those. But now we're kind of introducing these ones may be green later or may be red later, but we don't know. And people get worried, well, we don't know what to do about it. So there's these guys have done a lot of research into answering like how bad of a question is that, and that's like what this table is showing.
Yeah, I think this is really helpful. Like this is a great analogy. And so basically the second row here is kind of giving you a limitation of how many envelopes can you open per second? That's a great way of visualizing it. So this is like for new incoming things. And then the last one is about knowing, like, first of all, of course, you immediately drop all the red envelopes. You just don't keep them around, and then you only keep around the green ones. And you just want to make sure you have like a very cheap way of understanding when they turn red, right? Like you don't want to basically have to, after every block, have to go through all of your transactions, because then instead of just every second like a few new incoming transactions, then all of a sudden every second you would have to process thousands of transactions. So you really just want to have like a very simple way of understanding, is it still green or isn't it? This is really what it's all about, basically.
Yeah. So
And
right now,
why is that different with the account abstraction versus like how it is today?
sure. So that's actually kind of what I was going to get into. So right now, valid transactions can turn invalid, but in very well-known and specific ways. So the two that I'm most aware of, and I think they're the only two, but correct me if I'm wrong, are when the account's nonce changes or when the account's balance drops below the value sent in the transaction. And those are the only ways that currently transactions can become invalid or the envelope can go red. With AA, there's basically an arbitrary way that the envelope can go red, that the transaction can become invalid, and that's according to the contract. And we need to make sure that those arbitrary ways are limited to predictable kind of ways, and that's what we're going to talk about in a bit, I think.
Yeah, if that makes sense, I think this is exactly it. So basically, and it's not even that it's two ways for legacy transactions. It's really like just one way, because you're right. It's either the nonce changes or the balance of the account changes. But for accounts, the only way that either the nonce or the balance changes is if you send another transaction from that account. So the only way you can invalidate a transaction right now is if you send another transaction from the same account. Like you can't invalidate a transaction from the outside. It has to be the same account that sends a different transaction, and then yours can become invalid that you keep locally from the same account. This is like the only circumstance. So basically every time a new block comes in, you basically only look at the accounts that send transactions in the block, and then you go back to your like huge pile of envelopes, and you've sorted them by account, and you only go to the to the 50 piles or whatever that had one of their transactions included in a block, and only for those small little subpiles that usually consist of like 1 to 10 transactions or something, maybe, you have to recheck the validity, right? Everything else just stays valid because it didn't have the balance or nonce decrease, or like balance decrease or nonce increase. If that makes sense.
So
Yes.
I got a question. So it seems like to me this all gets down to the double spend problem. So let's say if a corporation has an account and there's a person in the Western hemisphere with the keys for that and a person in the Eastern hemisphere that has the keys for that, and they accidentally double spend some money, and they both send a transaction in, and they both go into the mempool. And when they first both go into the mempool, they're valid, right? But then the first one, let's say the first one gets included in block N. And so when it gets included in block N, that one's valid, but then the other one's still in the mempool that didn't get included goes invalid. And so is it possible for that block N, and when N+1 goes on, is it possible between those two blocks for something to go invalid?
So between those two blocks, do you mean like in the sense that if it's
In
still
other
valid
words,
after block?
In other words, you don't want to double spend any ether. And for block N, if something has been spent before block N, then it becomes a double spend, and so that becomes invalid. But if something went in block N that spent some ether, and you've still got something in mempool that's going to double spend that ether that they both accidentally got in, you don't want that to go in block N+1 because it already got in block N. And so you don't want to, in other words, my question, it seems like to me that nothing could, in other words, you can't double spend that ETH. In other words, if you've already got block N and you know where all of the ether is at block N, and you can tell that there's nothing in your mempool, current mempool, or in other words, you're not putting anything in N+1 when you're a miner, and so you know that there's no double spending, and so it's valid. And so my question is, can something go valid between, in other words, if something's valid at block N, can it go invalid before N+1 goes on?
That's a good question, and the answer is very simple there, and the answer there is no. So you're completely right with the analysis. Like I don't think double spend is the only scenario in which kind of transactions that you keep locally. I mean, another word for double spend, it could also be replacement, transaction replacement. It's only not only if two people hold the same key, but also if you just bump the price,
nonce,
right?
Yeah, or
yeah,
same, yeah.
Yeah. So basically just exactly. Or you could even have some like a transaction, you send transactions with nonces 1 and 2, and then you kind of send a competing transaction with nonce 1. Then that could invalidate both other ones or something. But again, yeah. But you're completely right in that once you have processed block n, there's nothing that can happen before block n plus 1 comes around that changes anything about the validity.
Okay, just wanted to make sure that was clear.
Yes.
That's what I was assuming. Just wanted to make sure that was the correct.
No, that is good. But this, of course, that is important. That also doesn't change with account abstraction. So basically, the ground truth of the blockchain only changes in the block interval. So every time a new block comes in, the state of the changes, but then between blocks it stays constant. So any assumptions you have after processing a block remain true until the next block comes in. And so basically, regarding your mempool management, basically this interval of a new block comes in, this event, that's the one that triggers the important reorganization, usually. Okay, but then, and I just want to basically reiterate before we can go to the solution, that we kind of understand the issue with account abstraction here, because that's what Sam pointed out, but it's really important. Account abstraction means any contract can basically send a transaction. So they can basically do any arbitrary computation and then call pay gas or not call pay gas. And arbitrary computation can really be arbitrary computation. So there's just no, it could access any state within the whole network. It could do whatever, right? Whatever unpredictable code path before it reaches pay gas or not. So there's just no way of knowing in the like the general case. Of course, now we'll talk about how we can actually deal with this. But in the general case, if you allow all kinds of transactions in your mempool, like AA transactions, every time the global state changes, and it changes every block, all of them could have turned red. You just don't. You'd have to really go back and re-execute all of your account abstraction transactions in mempool at that point. If you do it like naively, and this is basically just like a long way of saying this is not something you can do. You can't just, if you want to have like a functioning node, you can't just keep every single account abstraction transaction that looks valid in your mempool. So what can you do about it? Well, I think so basically the idea is really simple. We already talked about if you were to just ignore account abstraction at all, then you wouldn't have an issue. It's really just about that you're accepting all account abstraction transactions in your mempool. Well, solution is simple. You don't allow all account abstraction transactions in your mempool. You basically have like very strict rules that tell you if an account abstraction transaction is safe. So basically, if it has predictable behavior, and only in that case do you keep them. So you basically only keep a subset of safe account abstraction transactions. This is basically the main idea behind our mempool rules approach here. So it's like all kinds of account abstraction transactions would theoretically be valid, but your nodes just only keep those that they can understand, basically. And the idea is
So to put that another way, you can mine any account abstraction transaction, but nodes will only propagate ones they know that are safe.
Exactly. So it's still basically on the protocol side, nothing changed. And miners could still, for example, if they have some way of being paid on the side, like people could pay the money to also process weird account abstraction transactions. But because they are paid on the side, they don't care, because if it turns out that it was invalid, they got the money anyway, right? So basically miners could still do whatever, but the network as a whole would basically only fall back to the subset of safe account abstraction transactions. And then basically our challenge becomes, how can we identify safe transactions? And the approach is kind of, I think, intuitive in that we start out with like a very restrictive set of rules where we only allow those that are like obviously extremely safe, and we have to first, of course, define what does it mean, right? But we start out with very restrictive rules, and we are very certain that those are simple to implement, and those work, and those only keep around transactions that are safe. And then from there, we have what's called these extensions to our account abstraction proposal that like kind of step by step try to add in more complex account abstraction transactions that are actually in fact also safe, but they are safe in some slightly less obvious way. And so the rules become more and more complex with these extensions, but also like the functionality that the account abstraction gives you, or like the subset of safe transactions give you, grows larger. So this is basically the two parts for the today's walkthrough that we want to do. Basically, first, briefly, it will be brief because it's a very small set of rules. Briefly talk about these simple rules and then talk about these extensions, if that makes sense. Yeah, so basically, I'm not even sure, do we have like further slides? I think, yeah, we already covered this, valid transactions invalid. I think that's doesn't really matter. Okay.
Sorry. I
No,
see
go ahead.
James has raised his hand. James, do you have to?
That was me. That was me in the beginning before I interrupted. I'll turn that off.
Sorry.
Awesome. So I think now is the time to kind of turn to the EIP, because again, the slides were more like for background. I think for PEEP and EAP, it actually makes sense to actually PEEP the EAP. And so here we are. So I think basically last time we actually got to this part. So like basically to the end of this part. This is like the protocol rules. So this is all of this above, the mining and rebroadcasting strategies. This is really just the basics. And now mining and rebroadcasting strategies, this covers how on earth can you identify safe transactions. And basically, I have to say, by the way, the EIP, it's still kind of mostly in the form that we first wrote it. I think at some point we'd probably want to go back and kind of restructure it a little bit, because since then we've of course had more and more opportunities to like this to just talk about it, and I think basically the overall structure of the idea became more and more clear to us as well. And so I think the EIP in its current form is not the clearest in explaining things, and so maybe we'll go back and kind of try and make that even better. But the idea is simple. So if you remember, we were just talking about when do normal transactions become invalid, and the point was they can only become invalid once they were valid in the first place, if the same account sends a different transaction. So the same account has to send a different transaction, then other pending transactions from the account could turn invalid, could turn red. And so our first approach is just, can we just kind of recreate the same like security assumptions, the same invariant for account abstraction transactions? Can we make it such that only other account abstraction transactions from the same contract can invalidate other pending ones? Because if we can, then well, hooray! Then we basically mempools can do the same thing they already do today. It's where basically they don't have to go through all of them. They know which ones critically could have turned red. And so how can we do that? How can we basically so there are two aspects of it. First,
That's really smart, by the way. I like that a lot.
Yeah, it's actually like it's interesting because it's like a funny story how initially we started out with account abstraction with like Vitalik's proposal from like I think in March or so. He just had a write up on I think on the ETH Magicians or something.
Yeah.
Where he just said here's a set of minimal rules. You could just go ahead and implement it or something. And that already had all of these ideas in there basically. And we just went ahead and implemented it. And then very briefly before we were ready to publish the EIP, we kind of got back together with Vitalik and got his feedback and everything. And I think he was the main person who actually like looked at it and was saying like, wait a second, do we need all these rules in the protocol? Can't we just pull them out and have them as like restrictions in the mempool? So yeah, all credits to him for that like twist. I think I agree though that this is like a really clever way of approaching.
And it's like, well, if it works if you do the same thing that works today, then it works.
Yeah, that's basically exactly it. Yeah, exactly. So like instead of being this weird new dangerous thing, just like think of it as just normal, like you already know it. Yeah, exactly. And even more restrictive, by the way. The basic version of account abstraction has the additional restriction that it says don't keep multiple transactions per contract, only keep one. This makes reasoning even simpler because you have to kind of don't have to deal with like sequential nonsense and everything. Just keep one, right? Per contract, only keep one transaction. And this is why one of the extensions is then called multiple pending transactions, because yeah, that's what it will do then. But okay, So how can we make sure only your own, like if you're a contract, basically, imagine you're a contract, how can you make sure only your own transactions can invalidate other ones from yourself, right? How can you get to this point? And it's actually two things. So first off is, and that's the obvious one, I think, is just don't allow the transaction, like the transaction to access external state, so state outside of your own contract, before it makes a decision if it wants to pay for the transaction, right? So basically, what does it mean to not allow that? Of course, on the protocol level, it's still allowed because, again, any kind of account abstraction transaction is valid. But in your mempool, if a new transaction comes in, it's an account abstraction transaction, you verify if it's even valid. If the contract is willing to pay for it, you execute it. Well, as soon as during this validation, before it decided to pay, as soon as it kind of wants to access external state, you just look at it and say, oh, it's not safe, I'll drop it. I don't care if it is valid or not. It's not safe, it doesn't look safe, I'm immediately dropping it. This is basically the whole rule here. And this is what most of the section is about. So this is like, we went through all of the opcodes that like can be used to access external state outside of your own contract. And the idea is just, if the execution hits any of the following, exit with failure. This is it. And this is, again, only for execution during validation. So if you process a block, everything is allowed, right, for transactions in it. But if you locally see a pending transaction, you execute it, it does any of these things that access external state, the kind of the block hash, the timestamp, the right, all of these things, wants to call some external contract, even like static call, delegate call, all of these things, it's just all not allowed, right? You just drop the transaction. You just don't care about the transaction anymore. And this basically gets us halfway. So what the invariant that enforces is your transaction, like the only state that you now have to be careful about is the local state of the contract, because other state is just not relevant for the decision to pay anymore. But there's still an issue. What about the local state? Well, for normal accounts, right? For normal transactions with normal accounts, the only local state basically is the balance and the nonce, as we were talking about, and they can't be changed from the outside. Well, the balance can be changed from the outside, but only in one direction. Basically, it can only be increased from the outside by other like transactions into your account. But increasing balance, it can't ever invalidate a transaction. So this is safe. There's only one way for external state access to your account, and that's safe. For contracts, of course, that's just not the case, right? Contracts, anyone can call into a contract and call any function in the contract, and of course, depending on how it's implemented, but the contract could do whatever state modifications. So let's say you have like a I want to pay Boolean in your contract, and that's true. And only if it's true, you're willing to pay for transactions. But then someone else calls a please disable payment function from the outside within a transaction, and then that just disables this Boolean, and then all of a sudden all the pending transactions become invalid, right? So this is also an issue. It's not only about you yourself not accessing external state, it's also about like the external world not accessing your state, or not at least not writing to your state. And now this is kind of a little bit more tricky, and this is one more of these kind of interesting ideas, I think. How can we prevent that? Because we are just like a single simple node in the network. We can't enforce what kind of things other transactions do, right? If a new block comes in and that writes to the state of the contract, we have no choice. We have to execute it, right? If it's a valid block, it's a valid block. So how can you look at an account abstraction contract and know that it can't be modified from the outside? And this is the key here. We just add another very restrictive rule, and then another very restrictive rule is just we define this bytecode prefix, and we only accept transaction to contracts that start with this prefix. So only if like an account abstraction transactions comes and it starts at a contract that starts with this is of course the Solidity equivalent, but like the bytecode, whatever the exact bytecode is, only if it starts with this exact bytecode do you keep it. And why this exact bytecode? Well, this is a little bit tricky, of course. I mean, the ERPs usually are written for conciseness, not for like ease of understanding. But basically, this is just a very weird way of recreating this kind of entry point address that, if you remember, basically account abstraction transactions always start at the like from the protocol point of view, always start at the entry point. So basically, this check just checks if the current transaction is basically an account abstraction transaction that just started, right? So basically, only if you're like within the very first step of the execution of an account obstruction transaction, only then are you in this case. So any external call into your account, this would always be false, because message.sender would always be the one calling into you. So this check basically can never be passed with external calls. So if during external transaction execution you want to call into the contract, this will always be false. And so basically, oh no, of course, this will always be true. I forgot about the not equals. So basically, this will always be true for external calls. And so if this is true, then you basically immediately return. You don't allow any state modification. The only thing you allow, like if you want to send the contract some ether, you are allowed to create a log that basically just says, I received some ether. That's fine, that's harmless, right? That's something that's just very helpful for a lot of wallets and whatever. But besides that, like people externally that wanted to modify, like if they call into a contract that starts with this bytecode, there's just no way for them to modify the state. Like every time they call into it, they are like immediately basically thrown out again. And this is interesting, right? Because now nodes can kind of enforce this without enforcing it, because like they can't stop things happening during normal execution, whatever, but they just know when they see a account obstruction transaction that targets a contract that basically self-imposed these restrictions to it. It's like I can signal that I self-imposed this restriction on myself, like on my contract, and only if you did that to yourself, basically, only then do I keep transactions for you around. And so this is basically, this gets us to this goal of like now being equal to, or like equivalent to legacy transactions. Because so what does it give us together? So you don't allow external state access, but you also don't allow external state to access you. Well, that just means that you're basically, at least for the purposes of your payment decision, you're just living inside your own bubble. No one can touch you. You can't touch anything outside. So it's like, as long as there's no transaction from your contract, you know that the state relevant for the payment decision does not change. And if the state doesn't change and the execution rules don't change, then of course the result of the payment decision will always be the same. So you see a transaction, you keep it in mempool, you know it won't change its greenness until the same contract sends a different account obstruction transaction. And so, ta-da, basically, now it's safe to keep those around. So yeah, probably makes sense to briefly stop here and just ask, was that like clear? Does that make sense?
So it sounds to me like you're extending the N. Once you have block N, nothing else can invalidate what you yourself are gonna, as a miner, are gonna put in N+1, and you're just sending that same rule to the abstract layer. So you can still say no one can invalidate the abstract thing that I'm doing. Is that right?
Yeah, I think that sounds right. Of course, I was a little bit. I'm not fully sure with this kind of this abstract layer, the way you're phrasing that. But I think at least if I understand your intention there correctly, then I would agree. Yes, that sounds about right.
So it sounds like you now have an opt-in process where you can where someone who's writing a contract or something can opt into making this be abstract friendly, and they can't lie about it.
Yes, that is like a perfect summary. And there's one more little wrinkle about they can lie about it. You actually have to kind of make sure they can't self-destruct, because otherwise they could basically recreate the same contract with different rules, and so they could actually lie. So this is one little asterisk that you have to keep in mind. But besides that's exactly it.
Yeah, cool.
Do you actually mind covering what self-destruct is? I know people in general don't like it very much, or at least in the core devs, I know people don't. And I'm wondering if you could quickly go over like what it is, and like what you're doing about that.
That's a great question, actually. And so you're completely right. Core devs don't tend to like set indestructible. It's one of these features that at some point was added, and then now it's like, well, we are stuck with it because a lot of contracts kind of use it, and so you can't just remove it again, or at least, I mean, there are people that just want to completely just disallow the opcode, but there's of course a little bit extreme. So what does it do? So it's very simple. So basically, a contract can just write, all it does is just execute bytecode, and so it just executes it like a sequence of opcodes. And there's this one opcode that just is called self-destruct. And so if you call this opcode, then basically what happens is your contract is immediately destroyed. So basically all the storage is deleted, all the code is deleted, the nonce is reset, and all the balance that might be remaining is sent to some recipient address that you specify with the opcode. So it's like just basically destroy this contract. This is what it does. And that kind of has a lot of it creates a lot of issues. So the idea was you want to allow people to kind of do a little bit of housekeeping, right? Because the state of Ethereum grows all the time, and sometimes maybe contracts aren't like used anymore. So maybe you could implement this functionality to just basically clean up after you don't need a contract anymore. But it created like a lot of issues. So for example, this, if you remember the Parity wallet thingy where they just had stuck funds, like a lot of stuck funds. I think back at the time it was like $100 million of Ether that was just unrecoverably lost, but because they actually overlooked some functionality that led into a self-destruct. And so someone self-destructed a very important piece of code that every single wallet was using. And so basically, it was gone, right? So yeah, self-destruct just creates a lot of issues. And again, with account abstraction, you just want to make sure if a contract looks a certain way, you just understand it won't change. And so we try to be minimally invasive in our workaround. So we proposed two different workarounds. The first one would just be modify self-destruct very slightly so that it doesn't change the nonce. And so why is that sufficient? Because the code could still be swapped. Well, at least right. I was being a little bit kind of broad in my statement, in that like self-destruct is an issue with account abstraction, because of course self-destruct can also only be triggered from the inside. If you have this prefix, then from the outside no one can get in and execute code, and so it can only be triggered from the inside. But we already were saying transactions from the inside, that's okay if they invalidate things, because that was the one thing that is allowed to invalidate things. So the main issue with self-destruct then was that you can also like kind of reset the nonce, and then all of a sudden you can basically recreate transactions with the same nonce, and that they have different behavior. And so like it invalidates like transaction hash uniqueness, and it just creates a lot of huge mess. So the minimally invasive thing would just be kind of prevent self-destruct from resetting the nonce. But the cleaner way, and the one that actually also gives us a lot of added benefits, and I already heard from a lot of teams that actually are interested in this functionality, just independent from account abstraction, that's this set indestructible opcode. So this would be actually, I think, would be the best way to go about it. Set indestructible is a new EIP that actually Vitalik was, and that's why it's 2937, whereas we are 2938. That actually came out of one of these pre-publishing brainstorming calls with Vitalik. Basically, just introduce another new opcode, and if you put that at the very beginning of your contract, basically, then the contract just can't be destroyed. It's like if you basically it doesn't even have to be at the very beginning, but that's where you kind of look for the opcode. But like if the opcode is called and then afterwards you call self-destruct, well, then nothing happens. That's the whole purpose of that's basically you're just, it's another way of these self-commitments, right? You self-commit to never use self-destruct, basically. That's what the opcode does. And so if you just put that, we would basically just modify the prefix that the very first thing it does is this set instructable, and then after it does the rest here. And so that way you just know it's gonna always look the same. That makes sense.
So then to be, I guess to summarize a little bit, are you saying that the set indestructible prevents like an internal code from calling the destructible? Is that what you mean?
Exactly this. So well, it doesn't. It basically, the moment that it does call this opcode, because you can't kind of change that you run into the opcode, but the moment you would call the opcode after you already, like the self-destruct opcode after you already called set indestructible, the transaction would just fail. It would not, in fact, destroy the contract. It would instead just fail because you did something that you were not supposed to do, which is fine. Which is then your own fault. If you want to fail, just fail. That's fine. Yeah,
and fail in this case means that they have to pay for their gas for the failed transaction, but nothing happens.
Exactly. Right? It just yeah, exactly this. It just reverts, but only back to the payment point, which for normal transactions is like the beginning of the transaction. For AA transactions, it's pay gas. You only ever revert to that.
Cool.
You brought up self-destruct, so I figured I'd also ask how this affects upgradability patterns. Like if a contract at one point of function is something, but then using the various patterns for upgradability, they want to change that. How does that interact with account abstraction?
This is a great question in that it also kind of it's like an ideal kind of bridge to the next and final topic. And I think we only have like 15 minutes left in the allocated window, so I think that's a good fit though, because the thing you usually use for upgradability patterns is not actually self-destruct, because you don't have to bother with self-destructing the old one. What you usually do is you have like an entry point contract, but that then basically just calls into some other location that holds the actual code. And then you just change the location where you call to change the logic that the contract uses. And usually you do this with this very specific call that's called delegate call. And so what delegate call, and that's, for example, when you use like in Solidity, when you write a library, that's what happens under the hood. So that delegate call is a way of calling a different location, like to basically execute the code of a different contract, but still within your own context. So it's still executed against your local state and everything. So it doesn't actually like go to the other contract and execute there. It only takes the code from the other contract and still executes at your local place, basically. And so this is the main thing that is like kind of used for upgradability for like these patterns. And this is basically right now with these very restrictive rules. It would not be possible to call this. I mean, actually, I'm pointing at it right now in the list of like disabled or like prohibited opcodes. You would not be allowed to call this before pay guess. So if you want to have like logic to decide if you want to pay or not, that is upgradable, you can't actually do that, because again, the issue is you would call you could basically call into some address, and then the address could just change, right, with self-destruct and so on. So basically, like if you had allowed this and the target location would change state from one code to a different code with self-destruct or something, then your envelope could turn from green to red without you noticing, because your local state doesn't change, but the state of the delegate call target changes. And so basically your question was, how does it interact? Is basically just upgradability not usable with account abstraction? And the answer is, well, you just have to kind of loosen your rules a little bit, because what I was just saying, like the only issue with delegate call is that the target could kind of change their state with self-destruct. Well, I mean, we already have the tools we need to prevent that, right? We just have to have this set indestructible EIP. And this is actually the very first thing we describe as like an addition here. If we have set indestructible, you can just allow delegate calls as long as the target of the delegate call starts with set indestructible, because then you know it is immutable. So then you can use it as code, because then the only way it could change is if you want to upgrade, basically, right? Upgradability only makes sense if you can actually have a way of upgrading. But upgrading again is like a call into your bubble, right? So you send an AA transaction, and that is allowed to do things, right? That is allowed to modify things. And internally it says, instead of this address for logic, now you use this other address. And that's fine, that is allowed. But then once you set the new address, then basically for any given address, the logic behind it will remain constant because of the set indestructible. So basically, short answer there, upgradability in the naive version, it would be basically, it wouldn't work. But this is what all the extensions are for. These are for exactly these kinds of use cases. Like, we would really want to allow for library patterns and upgradability. Well, just understand exactly why is it an issue, kind of find a less invasive version of preventing the issue, and done.
I get it.
So yeah, that makes sense.
And if it's only the case if you want to have it so someone else can call your upgradability, but like if I wanted to just do a normal transaction, and do I always need to have that be possible, or can I just do a normal version of it? That makes sense.
Well, so basically,
like if you had upgradability. Oh, okay. Oh yeah. I don't know. Never mind. Keep going.
No. I think let's do this. Let's basically put this question on hold, because I think there's actually like a non-trivial answer. if I understand the question correctly. So the question is, who can do the upgrading? Can it only be the user from the inside of the AA contract, or can you do it from the outside? And right now the answer would be, if you do this thing, then it's possible to do it from the inside, but you couldn't do like trigger an upgrade from outside of the contract. It would have to be like a transaction that starts at the contract. But actually allowing things from the outside is one of the other extensions. That's why I kind of was saying, let's put this on hold, because with one of these further additions, you'd also be able to trigger the upgrade from the outside, if of course the contract allows for such logic.
Okay, cool.
If that makes sense.
Yep.
So yeah, so I think it probably just makes sense to just briefly go through like the main extensions. So just the way it's structured. I think this is still the way we think about it mainly. It's like, as I was saying initially, just for mempool.
For a moment. So we're kind of nearing the end of the time, but I really wanted to cover. I feel like it's important to cover the security considerations, because I know that was a concern in the core devs meeting. Do we mind like really quickly going through this and then hitting to, or just getting like a quick summary, and we can always have another call as well, I think, if that's necessary, but so we can just really quickly get to security. Does that make sense?
You know, that is a great idea, I think, actually, because you're completely right. This is like the main thing that people are interested in, just on a high level, if they don't want to dive into kind of section too much. But I think actually like it's mainly the things that we kind of topic-wise already covered. So basically the idea is, I think the main slide here was this one. So basically, there are several things. So the first one is we are relatively confident. We are very confident that the actual protocol changes that we describe are very simple to reason about. So of course, one primary aspect of safety of new ERP is always like, does it change execution in a way that is unsafe? And our claim would be that it does not, in fact. So it only adds 2 opcodes. It adds a new transaction type. All of these are very well understood. And the nonce opcode is trivial. It doesn't have any security implications. The PayGas opcode is a little bit trickier, but of course, again, all it does, it pays for transaction. It creates this checkpoint. All of this. So basically, we put like a lot of effort into making sure that the actual protocol changes, we would be very confident that they are like perfectly safe and can be like implemented and vetted and everything with very little effort. This is like step 1. So like the actual protocol changes, I think we can be very confident that those can be done securely. And then the question, of course, is, and this is basically the topic from just today, right? Either just nodes would not support account abstraction transactions whatsoever, but then it's useless. So can you add support for pending transactions? So can you do the mempool side of things in a safe way as well? This is the only other, like the main, I think this is the only other security consideration there is. Protocol changes are safe, in my opinion, of course. And then can you do the mempool support as well in a safe way? And there, our argument, like the way we kind of want to build our argument is, this is like a more complex topic. So idea is, we have this basic version. This is only like the single tenant, what I was just describing, the opcode restrictions, only 1 pending transaction, and this prefix. These 3 together, I think they are simple enough that you can really you can reason through them, and you can see, if you were to only go with this basic version, then it is also safe from all these other aspects, these non-protocol aspects, like what about, so we did like in other presentations, we also had like some of these nice little visualizations that kind of contrast effort you spend on chain versus off chain, how you basically have to pay for effort that you cause on the network, and how that doesn't change with a transaction. So you still have this mechanism. So basically, the claim is, as long like with these mempool rules, as long as they are safe, well, as long as they do what they are supposed to do, then they are safe, basically. And this is, of course, a bit more of a involved argument. So I think this is one that people would have to vet more, because it's of course like something unusual to do these kind of mempool restrictions. But this is basically what the whole safety of account abstraction would basically is based on. So our claim would be that as long as you have good rules that reliably give you a safe subset of transactions, then the overall account abstraction system is safe. And furthermore, here is like a more and more involved list of safe rules to identify safe transactions. So basically, the main thing we would want to convince people is this base variant would be safe, and then for every single extension, we would also go ahead and argue exactly why is it safe to relax the rules in this way, or something like that.
So my follow-up to that would be like what, okay, actually first off, does anybody have any questions or want to say anything? I think James.
Yeah, I think something that we didn't really explain well that we could is like where, like, say things went wrong, what would that look like? Like, and if a node is getting all these envelopes and is opening them, where the security or the DOS vector or the problem would arise is if a node has to open up more envelopes and if it keeps having to go back and open up envelopes to the point where it can never actually get anything done, then you have a network that can't pass transactions, that can't process blocks, and that would be like the security problem. Is your network is overrun with transactions that are turning red, green, and the node isn't able to keep up with the number that are coming in, and you just kind of slow down to a halt.
What about like bad nodes as well, actually? Like, couldn't you have a node that lets invalid transactions come and then just like clog up the whole network in that way?
As long as it's
Yeah.
not forwarded by valid nodes, then the problem is isolated to just the direct peers of that misbehaving node.
And make sure that I got that right, or if that made sense, Ansgar. Or
Yeah, so I think I totally agree with your framing there. Basically, I think so. The first step in our reasoning is that we kind of try and reduce it to kind of at least failure cases or like problem cases that we are already familiar with normal transactions, and then we can just basically, then it's just like a empirical question: how much worse is it with a kind of abstraction transaction? So, for example, invalid transactions, spam a node with transactions with invalid signatures. You can already do that today, and it's already a potential issue. If you just send a lot of transactions with invalid ECDSA signatures, this will temporarily take out a node. So the question is, how much of an issue is it today? How much of an increased issue is it with account abstraction, because account abstraction is more expensive to validate, basically. And this is exactly what this, if we go down to the security considerations, this does write up. And of course, this was the first write-up we ever did on account abstraction, so it did use like a lot of early assumptions. So it's not fully 100% kind of on point anymore, but it like the main points hold. So what we actually did is we tested exactly this. So how many transactions can we send until you reach this capacity? And it's basically, it is fewer transactions that can reach that point, of course, because it's more expensive, but it's not that many further. So it's maybe like a factor of, I don't have the, of course, depends on the gas limit or something, but I think it was like something, maybe a factor of 10 or something.
Well, and we also determined that you can configure your gas limit. It's not something that has to be set for everyone. So if you're running on like a Raspberry Pi 2 and it's like a terrible computer, you can set a low validation gas limit to protect yourself, and that won't hurt everybody else.
Exactly. So it's basically, the idea is try and kind of reduce it to the same kind of issues that we already know, and then just figure out how much worse is it, and is it reasonable or not. And this is also this approach with this. Of course, there's a little bit trickier because it isn't really as much of an explicit issue today. But this is why we had these slides where, in theory, where we talk about or already today, in order to invalidate transactions, you have to actually send it a valid transaction on chain that does something, and you have to pay for that on chain. And so, how much gas on chain do you have to spend to basically invalidate gas off chain? So that's at least the way to think about it. And basically for account abstraction, we also have this exact same invariant. We just have like a ratio, and I think in the EIP we even explicitly kind of give this a name, this ratio. Yeah, it's basically the verification gas multiplier. I think is basically what you say, like how much more gas offline can you invalidate by spending gas on chain? And if you have this kind of upper limit there, then you're kind of safe, because then it's always predictably expensive to cause issues locally, and that protects you against DOS there. So, but of course, I mean, this is all our internal reasoning. So or mostly internal and so on. So of course, we might be off here. But basically, we were trying to kind of make it as simple to reason about as possible with these things.
You guys should give yourself some credit. This is like a really elegant solution to the general problem. Like the general case is just like, oh my goodness, there's nothing you can do. And this is like one of those mathematically beautiful, awesome stuff that people come up and you're like, oh yeah, of course.
Yeah, and it's actually interesting. I mean, again, we were probably running. We have to come to an end soon, but like every single time we prepare for a new presentation or something, we kind of still understand the properties like better, because I think a lot of this kind of this fixed ratio kind of aspect of it, I think we only understood when we fully understood when we prepared for the Gitcoin presentation we did recently. So it's a kind of very non-trivial topic, and so I mean again, of course, it's one of these EIPs where I think it's absolutely uncertain if it will be accepted on mainnet or not. I mean, I would argue for it. If we ever have like 6-month period where there's nothing else to work on mainnet, I would definitely push for, let's now talk about a kind of abstraction, let's actually get it done, because I think it's simple enough, or this version is simple enough that it's feasible, but it definitely will take like quite a bit of attention from all participants. And right now, of course, we have Berlin, then after we probably have 159, then after we might have statelessness, then after we might have the merge, and then maybe like at some point, or if like one of these things gets delayed and there's just a big gap, then I would kind of try and jump in and I think then we would try and push for this again. So this is where we're at, and we actually, I think we are later today we have a call with the Optimism rollup people to also talk about like, how do these things make sense in a rollup context? So maybe we'll just see it in a rollup context even before it hits mainnet.
Well, that would be awesome.
Yeah.
Yeah, I mean, I would definitely think so.
Yeah. So while we are talking about this, like, getting into mainnet and EIP, and this particular show is all about EIP. And we also have an EIP editor, Matt, with us. I would be curious to understand the readiness of this proposal to go to the next level. Like right now, it shows that it is in the draft status, how ready it is to go to the like review or maybe to the last call.
So there are a few technical issues that still need to be decided. One of which is whether we change the behavior of self-destruct versus requiring set indestructible. That's one undecided question that we have. There's still a few other small points on like what tx.origin returns at different call levels that still needs to be discussed, but they're all very minor, like finer details that I think we can resolve very quickly.
Sounds good. Like I know that this proposal has already requested to be considered for inclusion. Is there anything that the authors can do, or maybe the editor can suggest here?
And just for full conflict of interest disclosure, that editor is also one of the authors. So
Something just that might be interesting for the readers is right now what's being worked on is the abstract transaction envelopes, and you would need that before clients implemented this, but that is going into Berlin.
Yes, and that happens to also be one of these topics that Matt is actually one of the main people involved with. So we have this additional advantage of just having that very like close to the effort, like someone very familiar with these kind of topics as well. Yes, but yeah, and I think just to very briefly for the kind of the governance process of the EIP, I think it's somewhat unusual in that I think a lot of EIPs, they're just, as soon as they are ready and all of these technical questions are answered, then they're just basically queued, and then as soon as the next hard fork is scheduled, then they just basically include it by default unless someone has anything against it or something. This EIP, of course, because it just even once it's kind of finalized from the technical point of view, because it just still requires a lot of attention, I think it's in this stage where I'm not sure if it's basically what exact kind of label is the right one for it, maybe considered for inclusion or something, but it will always remain in this, it's maybe similar to ProgPower or something, where, well, I would be a little bit more optimistic about it, but basically where it's like, it's technically good enough or mostly ready or something, but we definitely need at some point to have like a broader conversation about it on the all core devs or something. So it's not yet basically just waiting to be included. It's just like considerable for inclusion. so it's different from I think most EIPs in that regard.
And that's mostly because of the scope that's put on, or correct me if I'm wrong, but mostly because it's the scope of the effort that client developers would need to take to implement it.
Yeah, I think that is exactly right. And
'Cause
implement it and understand all the implications, basically.
Yeah, understand it and then implement it correctly, because mempool is one of the most complex and hard stuff to write in clients, if my understanding is correctly.
Yeah, maybe the best EIP to compare to, by the way, would be 1559 at 1559, because it's just that this I think already has universal buy-in or almost universal buy-in. So I think once that's ready, it'll almost certainly go in, but it'll also like one of these things that just requires a lot of attention from the whole ecosystem to get it done. And so I think this is very comparable in the kind of the effort that it.
Yeah, and the
will
scope,
require.
I would agree with that.
Yeah, I think we're sort of going into uncharted territory here, where we haven't seen changes this radical to the ETH protocol, since it was considered a production chain. And so I'm particularly curious, like it's been very interesting being a part of 2718, seeing how that is progressing through. And then I'm really curious to see next year how these things like 1559, binaryification of the state tribe, these things go. Because we're going to learn a lot about what it takes to make, large changes to a production blockchain while it's running.
Well, then I think that pretty much sums up today. I think that was a great ending point. Pooja, do you want to do an outro?
Yeah, of course. I mean, we probably went a little over time, but I think it was totally worth it. I'm glad that we decided to have this call, like the part 2 for this account abstraction. And the proposal, to me, it seems like it has a lot of potential and have exciting use cases, as it was explained in earlier episode, like smart contract, wallet, coin mixture, and DeFi protocols. And we discussed some of the questions this time in today's episode. I hope it would be helpful for dApp developers to implement this proposal in their project. And I would like to mention that we also had a community call on account abstraction last month. I will leave the link in the description section below for people to refer who haven't watched it earlier. And for people watching on YouTube, you may find Twitter's handles for today's guest and rest of the participants. If you have any question, comments, or concerns about this proposal, or any suggestion about the proposals that we could include in future episodes, feel free to leave a comment. While we are discussing about some exciting proposals to be coming up in 2021, I'm happy to announce that the next proposal that we are considering for PEEP and EEP is EIP 1559. We would be having a discussion with Timbaiko to understand what this proposal is and take some of the questions that people are curious to know. So stay tuned and don't forget to subscribe to the Ethereum Cat Herders channel for YouTube notification. Keep sharing your love with Ethereum Cat Herders. You can also join us on Discord. The invite link would be available for you in the description. We'll be back soon with another proposal. Till then, stay safe. Cheers.
Bye. Thanks, everyone.
Thanks, Ansgar. Thanks, Sam. This is great.
It was a wonderful conversation. Thank you, everyone.
Thank you, James.
Yeah.
Bye.
For having us.